Hello and welcome to Andrew Awesome. Today we are going to be doing the Mosaic model of the eukaryotic membrane. So the fluid mosaic model is a great model to demonstrate exactly what the membrane is made up of and how it works. So this would be the overarching theme of biology of, you guessed it, structure and function. So starting off, we are going to draw the channel protein. So that is our channel protein. And the channel protein has a pathway. And you're going to draw that pathway just like that. So we got a pathway right there. Okay. And the next thing that we're going to draw is we're going to draw phosphates. Phosphate right here. Negative P, obviously representing the phosphate. We've got our fatty acid, so this is our, yes, we got a fatty acid. So we got our saturated fatty acid right here. That's the saturated fatty acid. And then we have our unsaturated fatty acid right here. So this is unsaturated because remember that it has the double bond right here, making that kink, which makes it unsaturated. And we're going to draw another, because it's a bi-layer, meaning that there's two layers of phospholipids. So we have two layers. And then we're going to draw a carrier protein on this side. So the carrier protein, we're going to have another pathway. And this time, we're going to have two dots in the middle, or two, yeah. And that's going to represent that with the carrier protein, when a molecule goes in, it kind of conforms to the shape around it, and then it'll come through the other side as to the channel protein, which is just a fixed shape, and any molecule with its size and polarity can go through. But we'll talk more about that later. So this is also going to be the glycoprotein right here, because we are going to have some glucose. So right there, we got a glycoprotein. I have to be labeling, so we're going to label this one, as we said earlier, the channel. Sorry, I'm gonna. And then we have the negative P, which represents phosphate. And then this is our carrier protein. Okay. So the next thing we're going to do is we're going to draw some more phospholipids. Another phospholipid. So we have our phospholipids right there. But the thing is, with this, what's gonna fill in this gap right here? What's gonna fill that in? Well, we're gonna have, of course, our favorite cholesterol fill that in. So, reality is, it doesn't matter what shape you draw. The only reason I draw hexagons is because that tends to be the standard shape of what anything is, but it really doesn't matter what shape you draw. It's just as long as it represents something, you can label it, then that's fine. I just like hexagons, I don't know why. They don't have to be perfect hexagons if you should be like drawing hexagons too, because all hexagon is six-sided shape. 1, 2, 3, 4, 5, 6. So there we go. So that is going to be our 6 connected hexagons, which, as we know, is cholesterol. So cholesterol right there, guys. Actually, I probably shouldn't draw that because then that probably might mess up my model. But anyways, we have a cholesterol right there. And I'm gonna draw another channel protein right here. Just to close it off. Okay, and we're going to have a peripheral protein on one of the other, close to or on one of the other proteins. So we're gonna have our peripheral protein under the channel protein that we have on the left right here. So the next thing that we're going to have is we're going to have a negative charge on the bottom. So kind of like that right there, we have, you know, just negative charge. You know, it's right there, it's basic, but represents what it's supposed to. So I'm going to use a little symbolism right here, so I'm going to have a little heart. And the heart is, so over here, or not actually over on here, I'm going to write a little key type of thing. So the heart equals integral and transport proteins. So that means integral and transport proteins. So we want to notice that this is also an integral and transport protein, as is the other proteins. So anyways, back to the peripheral protein. So we're going to have a cytoskeleton protein, which comes off of the peripheral protein. And there's going to be more cytoskeleton proteins. So we'll have one that goes like right there. We'll have one that comes over here. We're going to have our cytosol. And we're going to have our hypertonic concentrations. So our hypertonic concentration is going to be a hypertonic concentration of H2O I'm going to use a different color so that it's not really... Alright, so we're going to have hypertonic concentration of this. We're going to have a hypertonic concentration of CO2. We're going to have a hypertonic concentration of an ion of potassium. Okay, the next thing that we're going to have is hypertonic concentrations on the other side. So, hypertonic concentrations of an ions of sodium. We're going to have hypertonic concentration of O2. Whoops. There we go. Have hypertonic concentration of C6H12O6. And we're also going to have some extracellular matrix proteins above this. We'll kind of represent that as being our extracellular matrix proteins. Not to be confused with the top. So I'm going to fill this in to show what the extracellular matrix protein is. So little squiggly lines inside of this wavy little bubble thing is going to be our extracellular matrix proteins. So I would say that this is a pretty, I might just add actually here, fatty acids. Other than that, I think this is a pretty decent. And continuing with our fluid mosaic model, we're going to write a context sentence about this wonderful looking model right here. So with the context sentence, we're going to say that in a fluid mosaic model, the membrane is a fluid structure with a mosaic. I'm quoting the mosaic. I'm gonna continue back over here. It's probably better if you don't, but I'm out of room. Of various proteins embedded in or attached to the double layer, parentheses bilayer, of phospholipids. So in a fluid mosaic model, the membrane is a fluid structure with a mosaic of various proteins embedded in or attached to the double layer, bilayer of phospholipids. So this is our fluid mosaic model, and thank you for watching Andrew Awesome, and we will have more awesome, well, awesome pretty much anything from school on here, so love learning.